Okay, so let's talk about data standardization. Data standardization in the Euclidean space is the standardization of attributes, and which is highly recommended so that they can have equal impact on all the computational distances. So if you want to compute the distance, and you need to compute the distance of all the attributes, of all the values in the attributes, so you need to make sure that they get an equal impact, the computation is correctly done and has equal impact on all the different data points. So how do we do that? Let's take an example. We take two data points, xi and xj, and we take the difference between them. So distance is equal to 700. Okay, so how is this 700 distance? It's a very large value. The range is very large, so we need to standardize our values so that we can fix a particular range, so that the distance always lies in that range. In future, it becomes easier to evaluate this distance if it is fixed, if it is in a range, fixed range. So in order to ensure that the attributes have a common value range, we can also fix the distance range as well, which will be easier to plot the distances, to measure and to evaluate it as well. So how can we standardize these values? How can we standardize the attributes? We know that there are two types of attributes and different approach will be used for them. In the case of numerical attributes, we have interval scaled attributes. What we mean by that is that, for example, if you have attribute called age, the difference between the age of 20 and 10 is the same as 50 and 40. So the scale has no effect on the interval. So these types of attributes, which are numerical in nature, can be standardized using two approaches. One is the range and the z-score. So if f is an attribute, we can find the range and the z-score for it. So the z-score, what it does is that it transforms the attribute values so that they have mean of 0 and mean absolute deviation of 1. So in this way, the mean absolute deviation is denoted by SF as follows. So this is the formula for z-score. So the same process, if all of these values have mean 0, which mean that they are become more centered, and the spread, since the standard deviation is 1, the spread is more normalized. In this way, it becomes easier to perform operations and computations as well. So the other type of numerical attribute is the ratio scaled attributes. It is also a numerical attribute, but unlike the interval scaled attribute, their scales are exponential. For example, the amount of microorganisms that evolve in a time t is approximately given by ae raised to the power bt. So for this particular case, we apply the logarithmic transform to the scaled attributes to normalize them. So it's important to remember and treat the ratio scale and the interval scale differently. If you get a ratio scaled attribute, you will apply the logarithmic transformation and standardize these attributes. So we have seen the ratio scaled and interval scaled numerical data types. Now let's move on to the nominal attributes. So whenever we're dealing with nominal attributes, we need to understand that there is sometimes a need to transform the nominal attributes to binary attributes, so that we can only deal with two classes. So the number of values of a nominal attribute is v. We create v binary attributes and we represent them. So if a data instance for the nominal attribute takes a particular value, the value of its binary attribute is set to 1, otherwise it is set to 0. So to take an example of this is, let's suppose that you have three fruit values, apple, orange and pear. So we have a nominal attribute fruit and it has three classes, three values. So we can create three binary attributes called apple, orange and pear individually rather than the only one which we had fruit. We study the same thing in feature engineering when we saw that we can convert one particular feature into different features using dummy variables. So this is the same concept over here. So we're dealing with nominal attributes. In order to convert them into binary attributes, we use the same technique. So after we create these three new features in the dataset, if a particular data instance in the original data has an apple for the value, then the transformed feature in the apple attribute will also have 1. And we will do the same for orange and pear as well. So this is rather a simple process to do it. So the ordinal attributes over here, then to remind you, the ordinal attributes are the nominal attributes which have a certain order to them. So what we do is that in the case of ordinal attributes, we treat them as interval scaled attribute and we apply the same z transform function to normalize them. Okay, so moving on, let's talk about handling mixed attributes. So we have seen so many different attributes and we have seen so many different functions to deal with different attributes. So far we have seen the 6 types of attributes: interval scaled, symmetric binary, asymmetric binary, ratio scaled, ordinal, and nominal. So let's suppose that you have given in a data set, there is a very high possibility that you have all of these data types. So how do you deal with different attributes of the data? One common way is to convert all the attributes to a single attribute. But the question is, how do you decide which one is the dominant attribute? And after decision, how do you convert all the other attributes to them? So let's suppose that given a data set, the most common or the most frequent attribute or the dominant attribute. So the dominancy is described by the frequency of the data set, most repeated attribute. So let's suppose that the most repeated attribute is the interval scaled attribute. And we want to convert all the other attributes into the interval scale attribute. So in order to do that, firstly convert the ordinal attributes and the ratio scaled attributes to interval scaled attributes. Okay, so the ordinal and the ratio scaled are converted to the interval scaled, and it is also appropriate to treat the symmetric binary attribute as interval scale attribute. So now the question is, how do you convert them? Actually, it does not make much sense to convert the nominal and asymmetric binary attribute to interval scaled. But in practice, it is quite frequently done, and it is done by assigning some numbers to them according to some hidden ordering. And that is also dependent on the context of the problem. Another way to do that is that we can convert a nominal attribute to a set of symmetric binary attributes, which are then treated as numeric attributes. So the next approach is how to combine individual distances. So if we don't want to convert all the attributes to a single attribute, the second way is that we can somehow get robust distance function which can be applied to all the different attributes. So let's talk about combining individual distances. So this approach, what it does is that it computes the individual attribute distance and then combines them. Looking at the algorithm, what it is doing is that first let's see that the distance values is always between 0 and 1. R over here is the number of attributes. So we are going over the attributes, we are iterating over the attributes. And what we're doing is that as the sigma f partially ij, or you can say y, is what it's doing is that it is the frequency when both the values of both the attributes is 1. So the indicator is 1 when both the x and xif and xgf, both the values of attributes, are non-missing, and it is set to 0 otherwise. So if they are available, then it is set to 1. If they are missing, either of them are missing, then it is set to 0. The other condition of setting it to 0 is that if attribute f is asymmetrical and the match is 0, 0. Equation 25 cannot be computed if all sigma fy's are 0. In such a case, some default may be used or one of the data point is removed. The dfy is the distance contributed by attribute f, and it is in the range of 0 and 1. So in this way, we can compute the distance of individual attributes and then combine them as well. Okay, let's talk about which clustering algorithm we should use when we are dealing with unsupervised machine learning problem. So how to choose a clustering algorithm? So clustering is a vast research. It has a long history, and there are a huge number of many algorithms that are available. We have only introduced the most common ones. So choosing the best algorithm is a very hard challenge. So the thing we have seen over here, that we have specific distance functions for specific data attributes. So what we learn from that is that every algorithm is dependent on the problem we are dealing with. And we've also seen that every algorithm has limitations and works well with certain data distributions. We saw the problem of k-means with the outliers. We saw the problem of hierarchical clustering of single link and complete link methods, depending on the chaining effect, and the outlier problem as well. So we know that every algorithm has its limitations and it only works well with certain data distributions. So it is very hard, if not impossible, to know what distribution the application data follow. And it is often possible that it may not follow the ideal structure or distribution which is required by our algorithms. So the first thing we need to understand is our data distribution, and then which type of algorithm should we use. Also, there is the problem of standardized data. We need to standardize everything. We need to standardize the data set as well. And so these are the things we need to study before understanding, if not choosing, the best algorithm for clustering. So there are certain complexities. Due to these complexities which we have seen, the most common practice is that we take a number of clustering algorithms and we start using them with different distance functions. And it is like exhaustive search. It's not just completely exhaustive. You use some industrial knowledge and you use the domain and you do some research and you understand, okay, these set of algorithms have the highest chance of performing well on my data set. So you start running these several algorithms with different distance functions and parameter settings, and you see which works perfectly by carefully analyzing and comparing the results. But the takeaway from this is that you need to remember that the results are based on the insight into the meaning of the original data. Okay, so along with the algorithms used. So we can conclude that clustering is highly application dependent and to a certain extent subjective. Okay, let's talk about cluster evaluation. Cluster evaluation is a very hard problem because we need to come up with a metric to quantify the quality of a cluster. So the problem over here is that you need to remember that we're talking about unsupervised data. We do not have the ground truths or the correct labels of the clusters. We don't even know if there are clusters. So some methods to inspect clusters for their evaluations are, we need to study centroids and spreads. We can also use rules from decision tree. For text documents, you can have someone read some documents in a cluster and tell them to see if there is some similarity between the documents. So this is some very hard grunt work. Another way is to use a ground truth. So the assumption over here is that we use some labeled data and that each class is a cluster. So after we have clustered and the algorithm is complete, we use a confusion matrix and we compute various measurements, which include entropy, purity, precision, recall, and F-score. So let's talk about entropy. So the entropy for each cluster, we can measure its entropy as follows. We can use this particular formula. So where the PR index I, bracket Cj, is the proportion of class Cj data points in cluster I or Di, the total entropy of the whole clustering is defined by this. The other evaluation measure is purity. This again measures the extent that a cluster contains only one class of data. The purity of each cluster is computed by this formula. The total purity of the whole clustering, considering all clusters, is defined by this. We can also conduct evaluation based on internal information. If you remember, we studied about intra and inter clusters. So we can see or measure the intra-cluster cohesion, which is also known as the compactness, which measures how near the data points in a cluster are to the cluster centroid. So the same method for doing that is we use the sum of squared error and we measure the intra-cluster cohesion. And the second is the inter-cluster separation. So the inter-cluster separation, or also known as isolation, separation means that different clusters, the different cluster centroids, should be far away from each other as possible. So we measure the distance of these clusters and they should be far away as possible. And that's how we can use the internal information of these clusters to evaluate them. But like I said, it is entirely application dependent and to some extent subjective, which means that most of the time we have researchers and PhD machine learning engineers who have tons and tons of experience. So most of the time there are just expert judgments is the key, because no one has so much time to evaluate clusters. So you just take someone who has conducted research on clustering for over the past 5 years, and I guess his opinion might be the right one. Okay, so let's talk about discovering holes in data regions. So what are these holes in a data space? So all the clustering algorithms, they only talk about grouping data. They study one intrinsic feature, which is the distance, and based on that metric, they group the data together. So what they're doing is that they're only representing one aspect of the knowledge in the data. Another aspect that we have not studied is the holes. These holes are the regions in the data space that contain no or few data points. So the reasons for that is that maybe we have insufficient data, or certain attributes combinations are not possible, or they are very quite infrequent or rare. So the question is, how much this aspect of the data is useful and how we can utilize it. So although clusters are important, holes in this space can also be useful. For example, let's consider a database of disease. We may find that certain systems and or test values do not occur together. When a certain medicine is used, some test values never go beyond certain range. So let's imagine a new type of disease has discovered, and the only way it is discovered because of the nature of these holes in the dataset. Because if we're talking about certain symptoms and they're plotted and they're being clustered, they do not occur together. If certain systems do not occur together, they represent very crucial information about that disease. And that might be very crucial to create medicine or vaccine for it. So data regions are basically empty regions. Given a data space, separate data regions and empty regions. The data regions will be called as clusters and the empty regions will be called as holes. So the empty regions have very less or no data points. So let's talk about how we can identify them, how we can use them. So we use a supervised learning technique, for example, the decision tree. So we use it to separate the two types of regions. Due to the use of a supervised learning algorithm for an unsupervised learning task, an interesting connection is made between the two types of learning paradigms. This is supervised learning for unsupervised learning. The decision tree algorithm is not directly applicable. It needs at least two classes of data. A clustering dataset has no class label for each data point, and we need to remember that. So the problem can be dealt by a simple idea regarding each point in the dataset to have a class label y. So we can label out all of the data points as the y label. And then we assume that the data space is uniformly distributed. This data space is uniformly distributed with another type of points called the non-existent points. We give them the class n. So with endpoints added, the problem of partitioning the data space into data and empty region becomes a supervised classification problem. Now we can use a decision tree to separate these two regions. So looking at this example, we have two clusters over here. This is the original data space. Then we partition them with added endpoints. A decision tree method is used for the partitioning, and we add endpoints which are non-existent. They don't exist, but we add them to make this unsupervised learning problem into a supervised learning problem. So the characteristics of the approach is that it provides representations of the resulting data and empty regions in terms of hyperrectangles. We can also call them rules. So it detects outliers automatically. Outliers are data points in an empty region. So it may not use all attributes in the data, just as in normal decision tree for supervised learning. It can automatically determine what attributes are useful. The drawback for this is that data regions of irregular shape, which are not hyperspherical, are hard to handle, since the algorithm we're using, the decision tree, only generates hyperrectangles. Okay, so let's summarize what we have learned so far. Clustering has a long history and is still active. There is so much research being done, and there are a huge number of clustering algorithms, and there are more still coming every year. We only introduced several main algorithms, and there are many others. There are density-based algorithms, subspace clustering, scale-up methods, neural network-based methods, fuzzy clustering, co-clustering, etc. Clustering is hard to evaluate but very useful in practice. This partially explains why there are still a large number of clustering algorithms being devised every year. So unsupervised learning is a very hard problem, and the algorithms introduced to deal with this problem are hard to evaluate. So the last point is that clustering is highly application dependent and to some extent subjective. So we used clustering for certain applications that have a lot of the data distribution of these applications must be accepted. So clustering is highly application dependent and to some extent subjective. We have seen that every problem and every domain specific, you can say every problem has a different clustering algorithm. So it entirely depends on the problem and on the application.